It's okay. Thank you. No, it's okay.
Okay.
It's okay.
And okay, let us start because Stuart is, yeah, we have to be today on time. So I am Sebastián Bergeret from Material Physics Center in San Sebastian, and this is our Josephine seminar. Josephine is a EU-funded project which focus on high temperature Josephson junctions as to act as artificial neurons and synapses. And we have this seminar. This is our fourth seminar. And today is a great honor to welcome Professor Stuart Parkin, who is the director of the Max Planck Institute for Microstructure Physics in Halle. Stuart is probably most of you know him. He's a world-leading expert in spintronics, nanoscience, so groundbreaking contribution, I would say, in transforming information storage technologies. And okay, he has over 700 scientific papers, I counted, I don't know, 120 patents, and he has been elected in prestigious academies worldwide, including, in addition, several prizes. So his CV is online, so I think it's impressive what Stuart has done scientifically. Today his talk is about superconducting spintronics for racetracks memories, and I think according to his abstract, he will explore how superconducting materials can be combined with magnets and enable next generation, maybe of cryogenic memories or logic devices. So with this, I'm pleased to hand over to Stuart. Welcome, Stuart.
Okay, thank you very much, Sebastian. I'm very honored have been asked to give this seminar. And in this seminar, as Sebastian mentioned, I want to tell you something about how we want to use superconducting spintronics, in particular, to build a cryogenic racetrack memory. So what I want to do then at the beginning of my talk, I actually want to introduce racetrack memory, what it is, and then towards the end, I'll get towards the superconducting aspects of our work. And here in this drone video, you can see some of the laboratories that we've been building in my institute since I joined Max Planck in 2015. And then we started building these labs in 2018. And then we've mostly finished. And this actually, what you can see now is a system of thin film deposition systems where we can build complex structures at the atomic scale. And in particular, we're very interested in interfaces and proximity effects, as I will discuss, between superconductors, conventional superconductors, and magnetic systems. So I wanted to first of course, acknowledge the students and postdocs in my group at the Max Planck who've contributed to this work. And this is actually a recent photograph of my group and the scientists and students and postdocs. And highlighted are in green and purple are the postdocs and scientists and students who've contributed to some of the work that I will discuss. Now, of course, I wanted just to give one page of introduction, which is that a general picture is that we, of course, are living in the age of big data, and that big data has to be stored on devices. And my talk really is about how we can build novel devices for storage. In fact, my whole career has been involved with using novel physics to build devices that can store data in ways that were not thought of before. And in particular, this is an article from Nature a year ago where they pointed out that the large language models for artificial intelligence have essentially used up all the data in the world. So we need to create more data. Today, much of that data cannot be stored because we don't have enough data storage devices. And so I want to briefly then discuss this. And so my whole career, as Sebastian mentioned, has been in the field of spintronics. And spintronics, of course, allows us to build new forms of devices, in particular memory and storage and computing devices, and also synapses, which unfortunately I won't have time to discuss, but that's actually an important part of our work. And of course, we want to, in spintronics, to create currents of electrons which are spin polarized, and then use these currents to manipulate magnetization by taking advantage of the spin angular momentum that these currents carry. And what I want to point out at the end of my talk then is, potentially we can create new types of superconducting supercurrents that could carry angular momentum if we can create triplet supercurrents. This is one of our main research goals today. So just to remind you then, today 80% of all digital data is still stored in a technology that's 60 years old. It's the magnetic hard disk drive. And today, these hard disk drives use a technology, a spintronics technology, as the reading head, the reading element, to read the tiny magnetic bits that are represented here by these blue and red regions. They point magnetically up and down, and the boundaries between these regions have stray fields. And these stray fields are very tiny, but they can be detected using a spin valve structure that actually I invented when I was at IBM in the late 1980s and early 1990s. And IBM first introduced this device into a magnetic disk drive in 1997. But in 2007, the basic sensing device is the same, but the physics switched from spin-dependent scattering at interfaces to spin-dependent tunneling in a tunneling junction. And so here you can see a cartoon of a tunneling junction with two magnetic layers, blue and red, separated by the gray layer. And that gray layer is a very thin insulating layer formed from magnesium oxide. When you extract the current from a magnetic layer, it's automatically spin polarized because of the spin-dependent density of states in a ferromagnet, because of broken time reversal symmetry. And when the magnetic layers are parallel, these spin polarized electrons can find empty states of the same spin polarization into which they can tunnel, and the tunneling current is high if the two magnetic electrodes are identical. And when you switch the magnetic electrode from the red to the blue direction, then the current can be reduced. And these differences in conductance can be several 100% at room temperature. So these are today used as sensing devices in a magnetic disk drive, and together the metallic version, the spin valve, and the magnetic tunneling junction enabled a 1,000-fold increase or more in the storage capacity of these magnetic disk drives. Those disk drives now have reached the end of their technology roadmap, and so an emerging technology is to use the same tunneling junction as a memory element where you store information in the direction of magnetization of one of these electrodes, blue and red as shown here. And in fact, this is something that we first proposed in 1995, and it was only in 2019 that this became a reality. You can now buy this magnetic random access memory from the major foundries all around the world. So I want to briefly then introduce racetrack memory. This was a concept that I proposed in 2002, and the very simple concept is this, that if you introduce current into a magnetic material shown at the top, then the magnetic material will scatter electrons of one spin orientation more than the other spin orientation. And this actually was known about even in the 1930s due to Neville Mott. And the current then becomes automatically spin polarized through this spin-dependent scattering within the bulk of the magnetic material. So shown on the bottom left is a cartoon of a domain wall. And in this case, the magnetization in a wire is pointing to the right on your left-hand side, and to the left on your right-hand side. In between is the domain wall, which on the nanoscopic scale looks like something with mass and momentum. And as shown in this cartoon, the conduction electron, which is spin polarized, as it passes across the domain wall, it will adiabatically rotate its spin and transfer one quantum of spin angular momentum to the domain wall. And the concept is if we have enough spin angular momentum, we can basically cause the domain wall to move. And what I proposed was that if we have a series of domain walls, all those domain walls will move in the same direction by current pulses. And this is something that we first demonstrated in 2008. And then this is the concept. This is the racetrack memory, that if we have a vertical magnetic wire shown on the right-hand side or on the left-hand side, then this vertical wire can be magnetized in the red and blue directions. And by passing current pulses into the racetrack, you can move a series of magnetic domain walls around the racetrack, and one would move them towards elements for reading and elements for writing domain walls integrated into that racetrack. And so what I proposed was this type of device could have the capacity of a magnetic disk drive, but would be, of course, have a smaller form factor and be much faster and more energy efficient. And this, as I said, we basically demonstrated the fundamental concept in 2008. However, it's only more recently that we've been able to demonstrate this on usefully technologically relevant length scales. And so here, just want to, I don't have time to really discuss all the physics behind racetrack memory, but just to introduce a couple of basic concepts. What I showed you before in that cartoon for moving a domain wall was the use of something called spin transfer torque. basically just a magnetic wire or magnetic film, no other layers present, the current is automatically spin polarized through spin-dependent scattering. The polarization can be up to 70% in nickel iron, nickel cobalt alloys. And when the conduction electrons, which are spin polarized, cross the domain wall moves. That's spin transfer torque. But around about 2012, another concept arose of called spin, which is now called spin orbit torque. And in this case, the magnetic racetrack is built on this yellow layer, and this yellow layer is a layer in which charge current is converted to spin current through some kind of spin Hall effect. And typically, this is a chiral phenomenon. The charge current will develop spin current orthogonal to the direction of the charge current, and the spin polarization is orthogonal to that direction of the spin current and to the charge current. So the concept then is that spin polarized electrons, which are generated by this conversion of charge to spin current within this layer, can then diffuse into the neighboring magnetic layer, forming the racetrack, and then it will impose a torque through the transfer again of spin angular momentum, and it's called spin orbit torque because typically the yellow layer typically will have a large spin orbit coupling to generate these spin currents. That's the idea. And it turns out these spin currents you could generate this way are more efficient than the spin transfer torque. So in the case of spin transfer torque, the domain walls can be moved at speeds of 100 meters per second, we showed, and with the spin orbit torque, we demonstrated speeds of about 300 meters per second. And these are basically still what is possible today using useful materials. On the right-hand side, you can see at the top, we could integrate in principle a tunneling junction into the racetrack. So the racetrack now is one of the magnetic electrodes. Then there will be an insulating layer, typically magnesium oxide, and on top would be a counter electrode here shown in this greenish color. And that counter electrode is typically would be fixed in its magnetic moment direction, and as the domains move underneath, the magnetic moments in the domains would be either be parallel or anti-parallel to the fixed moment of that counter electrode in that tunnel junction, and then they can be detected very efficiently with huge signals in this way. On the other hand, shown below is a different way of measuring the domain structure using the enormous Hall effect. So there are a lot of Hall effects, as you're all very familiar. In this case, in a magnetic material, a ferromagnetic material or ferrimagnetic material, the charge current is converted to a transverse spin polarized voltage, which is the anomalous Hall signal. And that enables us to detect, I want to show you very tiny racetrack technologies. So over the last, since 2002, then the racetrack has evolved through very distinct, I like to call these four families of racetracks. In the racetrack 1.0, which is what we demonstrated in 2008, then in those cases we used very soft magnetic materials, nickel iron and nickel cobalt alloys, in which we knew that from the work from the 1930s and beyond, that the current is highly spin polarized through this spin-dependent scattering. And we could show that the domain walls would move at speeds of about 100 meters per second without significant heating of the racetrack. At higher current densities, then you start to nucleate domains due to temperature effects. In racetrack 2.0, we switched to a multilayer, typically of cobalt and nickel. These layers are very, very thin, so that the interfaces give rise to a perpendicular magnetic anisotropy, and these shrink the size of the domains from hundreds of nanometers in racetrack 1.0 to just a few nanometers in racetrack 2.0. And it turns out then the domain walls would move at roughly the same speed, 100 meters per second. So it's independent of the size of the domain walls. In racetrack 3.0, now we've introduced this yellow layer, which could be platinum or tungsten, or more recently, we've shown using some very special L10 iridium based alloy materials, we can achieve the conversion efficiencies of charge to spin of more than one, in fact, up to three, we believe. That means every electron will generate three spin polarized electrons. This enables us to move these domain walls much more efficiently, and in this case, the velocities that are possible are about 300 meters per second. And finally, the most interesting racetrack, 4.0, is where we showed in 2015, so all of this some time ago, we built what we called a synthetic antiferromagnet. In this case, I think you can see from this cartoon that you have a lower racetrack coupled through a very thin layer, which is actually typically ruthenium, a few angstroms thick, which couples the lower magnetization in the racetrack to the upper racetrack layer anti-ferromagnetically, so that the lower racetrack is essentially a mirror image of the upper racetrack, so that at any position along the racetrack, the upper and lower magnetic moments coupled anti-ferromagnetically have the same magnetization. So you can eliminate the moments so that there's no net magnetization. And as you can see in racetrack 1 to 3, you can see the stray fields from the domain walls are so large that they cause significant interactions between neighboring domain walls within one racetrack or the neighboring racetrack, which we showed by micromagnetic simulations. But the racetrack 4.0 eliminates all the net magnetization so that there's no stray field. And in these cases, we accidentally discovered that the velocity of the domain walls is significantly increased from 3.0. In fact, here, the domain walls we demonstrated could move at speeds of up to 1 kilometer per second. So this is extremely interesting. These are very high speeds, 1 kilometer per second for the same current density as in 3.0. And it turns out there's an additional, what we call a giant exchange torque, which derives from the very large anti-ferromagnetic coupling field between the upper and lower racetrack. Well, this is a brief introduction, and then I just wanted to mention that really all of our work for a number of years used optical techniques to detect the domain walls. So on the top here in 3.0, you can see a racetrack which is a few microns wide and tens of microns long, and the black and white correspond to the Kerr signal that we detect. The Kerr signal it's a magneto-optical Kerr effect where the polarization of light is rotated as it's reflected from the surface of the magnetic film, and the signal then is high or low, depending on rotated to one direction or the other, depending on the magnetization direction. So in fact, as you can see here, we take a static picture of the domain walls, and then we apply current pulses and take another static picture. This is how we determine the domain wall velocity. 4.0 is one of these synthetic antiferromagnets, and you can see there's much less contrast because effectively there's no net magnetization in this system, so the Kerr signal is much reduced. Nevertheless, we could demonstrate a series of domain walls moving backwards and forwards at speeds of about 1 kilometer per second. So the racetrack is a very interesting technology I mentioned earlier. It's all due to interfaces. And the interface between, on the right-hand side, you can see a cartoon. The green and blue layers are layers of cobalt and nickel. They're just a few angstroms thick. So the actual racetrack magnetic layer is 1 nanometer thick. Underneath is a platinum layer in this particular case, which is a few nanometers thick. And down below in the synthetic antiferromagnetic racetrack, we build the two cobalt-nickel-cobalt sandwiches sandwiched between them by ruthenium. And ruthenium is something I showed a long time ago in 1990, 1991, gives rise to a huge oscillatory interlayer coupling depending upon its thickness, and for very thin ruthenium, the magnetic coupling through a so-called Rudiment-Kittel interaction is anti-ferromagnetic. In fact, it's very, very large. It's about 1% of the exchange within the magnetic layers themselves. So then this system gives rise to these very large velocities of domain walls. So I just wanted to mention, and I showed you this drone video. In fact, if you look more closely, what you would see in this, what we built in the last 6 or 7 years, is a series of thin film deposition systems with which we can grow magnetic, non-magnetic, and superconducting layers. We have on the one hand some molecular beam epitaxy systems, and we also have this system we called Mango, which is a homemade system for magnetron and ion beam sputtering, which are techniques which allow you to explore a wide variety of materials. And we have 2 of these systems. Each system can contain up to 44 distinct sources of magnetron ion beam sputtering, and also we could exchange the subchambers to allow for evaporation, essentially molecular beam epitaxy, all in the same system. And then all these systems are connected. On the left-hand picture, you see this orange line. This orange line is a UHV ultra-high vacuum tube, 15 or 16 meters long, through which we have a little robot that carries substrates under automated control, and we can switch the substrate between these different systems again under robotic control. So we think this is one of the most advanced systems of its type, enabling us to build very complex systems. And then down below we have a glove box, and this I'm going to show you later on. We use that glove box to exfoliate 2D van der Waals materials. So now I just wanted to finally mention that for the racetrack, that of course to make these racetracks useful technologically, they have to be very narrow, on the order of 50 nanometers or less wide. And we've been able to demonstrate the motion of domain walls through racetracks that are only 50 nanometers wide by building this racetrack. This is actually a schematic cartoon to scale of a magnetic layer, which shows the blue and red regions, and the domain walls actually have a chiral nail structure determined by the interface with the lower yellow layer, which here is platinum. And we build the platinum layer, it actually is slightly wider than the magnetic layer. We call this a platinum wing. And we demonstrated that by experiment and by simulations, that depending upon the width of that platinum wing, we can detect the magnetization away from the position of the Hall bars, these electrodes, which you can see. And through one racetrack, we have a whole series of these Hall bars, allowing us to detect a domain wall as it moves along the racetrack. And by designing the width of this platinum wing, we can design the Hall bars so that we can detect a domain wall anywhere along the racetrack. And this is a paper we published in Science just last year, demonstrating that we could see the current-induced motion of single domain walls in racetracks that are only 50 nanometers wide. And so here, for example, you can see the signal from these anomalous Hall detectors, which we have built along a single racetrack. And this shows you when we introduce 5 nanosecond long current pulses, each pulse moves the domain wall a little bit, and enough pulses will take the domain wall from one end of the racetrack to the other, and then we switch the sign of the current pulse to move the domain wall backwards. And then we increase the intensity of the current pulse so that we need a smaller number of current pulses to take the domain wall from one end of the racetrack to the other. And so as you progressively, with these numbers of iterations, we're increasing the intensity of the current pulse for the same current pulse width, and you can see that the domain wall is moving faster, so we need smaller numbers of current pulses to take it from one end to the next. And why this is so remarkable is that we've gone from micron-wide racetracks, where we could optically detect the domain walls, to these racetracks, which are just a few tenths of nanometers wide, yet it turns out the domain walls move at roughly the same velocity for the same current intensity. And this was quite a surprise. We thought that the edges would be quite rough and that would deter the motion of the domain walls. It turns out that this isn't the case. So this is a very interesting point. And then we also realized that we could position one domain wall precisely along the racetrack with an accuracy of a few tenths of nanometers. And we could position one domain wall with respect to another one to about a position that we could put them close together to about 100 nanometer precision. So we believe these numbers, the ability to position a single domain wall to an accuracy of a few tens of nanometers in a very narrow racetrack, is basically what is needed to build a racetrack at the which is technologically relevant. Anyway, you could read more about that in this science paper. Now I want to switch then to superconducting spintronics. So first, I just wanted to point out actually some very nice work by Bozdin and actually our chairman, Sébastien Bergeret. And what this shows is simply this. The idea is, what happens if you place a conventional superconductor, which is typically a S-wave superconductor, if you place that superconductor in adjacent to a ferromagnet, what happens? Well, you're all familiar that in a superconductor, in an S-wave superconductor, then the superconducting condensate is formed from Cooper pairs. And the Cooper pairs have two electrons, which have opposite spin and opposite momenta. Now, what happens when you have a ferromagnet, as shown in this cartoon? You can see we have a blue and a red band that are exchanged, which are split in energy for the spin polarized up and down spin electrons by the exchange splitting, which of course is the Heisenberg exchange within the ferromagnet itself. And so the higher the Curie temperature, the bigger is this exchange. So now, if we want to form Cooper pairs with electrons at the Fermi energy in this cartoon, you can see that they would have distinct momenta. So to form a Cooper pair with electrons with opposite spins, they would have distinct, there would be a net momentum. And this net finite momentum gives rise to a very interesting finite momentum Cooper pairing state, which Sebastian demonstrated in the ferromagnet now consists of two components. You have a spin singlet conventional superconducting component, but you also now have a spin triplet component. Here, the spin triplet component will be in the s equals 0 state. Nevertheless, the Cooper in the Cooper pair, the two spins are basically parallel to one another. And at the same time, you have then, as you can see in this figure from which is taken from this review article by Escherick, then you can see the green singlet state would decay into the ferromagnet in an oscillatory fashion, and similarly the triplet state would be formed in the ferromagnet and would also have this oscillatory decay. And typically in the ferromagnet, this superconducting wave function would rapidly decay. However, if you make the ferromagnet very, very thin, then you will have a superconducting wave function that persists. And what Sebastian proposed was that if you have a second magnetic layer orthogonal to the first one, it would allow the traveling of triplet pairs, the triplet component of the superconductivity over long distances. So you could use this and long collinear magnetization to generate triplet supercurrents. So I just wanted to show you some of our own experiments in this regard, and this is by Ivan Kindiak, a PhD student of mine. And what he has done, he's built vertical Josephine junctions. So I understand that this Josephine seminar is based on Josephine concept. And in this junction, you can see in this cartoon, we have created a structure with a conventional S-wave niobium electrodes. These are 50 nanometers thick, two of them. And in between, we've got some copper to separate the niobium from the red layer, which is a nickel-cobalt multilayer. In fact, these nickel and cobalt layers, a few angstroms thick, essentially are identical to the nickel-cobalt nickel-cobalt sandwich I mentioned earlier was in the racetrack. So this is derived from our racetrack. Essentially, we have a racetrack separating two niobium electrodes, but here we're not considering domain walls. The racetrack here is magnetized all in one direction. Now, the idea is that if we now look at the critical, well, now the idea is we can actually pass a supercurrent from the niobium top electrode to the bottom niobium electrode through the copper and the nickel-cobalt multilayer. And on the left-hand side, you can see the black dots shows the critical current as a function of the thickness of the PMAs, the perpendicularly magnetized cobalt-nickel-cobalt multilayer. So because the layers are so thin, the magnetization is perpendicular to those interfaces, just as in the racetrack I mentioned earlier. And then you can measure a critical current density for this, shown as that the black circle for a certain thickness of that cobalt-nickel-cobalt multilayer. And as you increase the thickness, then you can see on the left-hand side, let's say we're going from just beyond 6 to just beyond 12 nanometers, you can see that the black critical current density decreases by more than an order of magnitude. For this, I'm going to call it a singlet structure. On the right-hand side, now we build a more complicated structure where we have the same nickel-cobalt multilayer in the middle, separated by copper from now a nickel layer. Here it's 1.2 nanometers thick. And there's a nickel layer above and below the perpendicularly magnetized cobalt-nickel multilayer. In this case, the nickel layer has a moment which is parallel to its plane. In other words, this one has no perpendicular magnetic anisotropy. So the nickel moment, the magnetization, is actually orthogonal to the nickel-cobalt magnetization. So we're going to call this the triplet structure, because now, following Sebastian's prediction in 2001, what we see is that we can actually create a triplet supercurrent that will actually survive over long distances, even though we've got more magnetic material on the right-hand side than in the middle. And on the left-hand side, you can see the orange dots correspond to the critical currents for this, what I'm calling the triplet structure. And you can see that for the same thickness of the cobalt, nickel cobalt multilayer thickness, the PMA thickness, the critical current density is increased almost by a factor of 10, but we've added more magnetic material, the nickel layers. And you can see as we increase the thickness again of the middle perpendicularly magnetized layer, you can see the critical current decays much less than for the singlet structure. So the concept here is that the orthogonal orientations of these magnetic layers allow for the generation and propagation of a triplet supercurrent over very long distances. And this is, we think it's a very nice experiment, but I have to say, these types of experiments were also carried out by a number of groups prior to us, but this is just confirming this concept that orthogonal magnetizations can generate long-range triplet supercurrents. At least that's the conclusion. Now, if we go to this next example, is something we think is very interesting, where for the first time we were able to demonstrate that we could pass or create a supercurrent passing through a system which is an atomically non-collinear antiferromagnet. And this is a very interesting system. In the middle of the foil, you can see a cartoon of the structure, and this has an hexagonal structure. This is manganese-3 germanium, and that structure has manganese moments, as shown as these blue and red dots, and they're separated by, in this case, germanium. And this forms a so-called Kagome lattice. This Kagome lattice has many interesting properties. It's metallic, but it also has a very interesting barrier phase component, which is an effective magnetic field that the system generates. And this leads to this type of material showing interesting properties such as an anomalous Hall effect. Even though there's no net magnetization in this system, due to frustration, the manganese moments are oriented in the plane of this system, but will be oriented at 120 degrees to each other, as you can see in this cartoon. And what does that mean? That means that what we demonstrated was, and this is work by Kunrock John, who was a postdoc in my group, who's now back in Korea, and what he demonstrated was that we could put the blue niobium electrodes, this is by electron beam lithography, we could place these on top of a layer of manganese-3 germanium, which we grew by sputtering, and we showed that we could pass a supercurrent through long range through the non-collinear antiferromagnet. So you would expect that these moments, the very large manganese moments, would destroy the Cooper pairs, but they don't. Rather, they allow the propagation of long-range supercurrents over very long distances, and we showed more than 150 nanometers, which is a long distance. And so we argued that this was evidence, the first evidence for an atomic structure, atomic non-collinear antiferromagnetic structure where supercurrents could flow over long distances. And so we argued we could see long-range spin triplet supercurrents in this chiral. It turns out it's a chiral antiferromagnet. On the left-hand side, you can just see this concept that you take a singlet superconductor, you form a triplet pairing, and then the non-collinear magnetization allows spin rotation and long-range spin triplet supercurrents. So we think this is a very interesting means of generating spin triplet supercurrents. And later on, I want to show you that what we want to do, currently what we are doing, is using those spin triplet supercurrents to manipulate magnetization. So one of these niobium electrodes we can replace with a magnetic electrode and use that spin triplet supercurrent to manipulate the magnetization in that second electrode. Actually, I'm not going to show you those data, but that's something that we believe we've now accomplished. So the last part of my talk is about a different phenomenon, which is a Josephine diode effect, and this involves 2D van der Waals materials. And so I thought I would just briefly introduce you to some of the work we're doing on these van der Waals materials. These are extraordinarily interesting materials in which you have layers which are strongly bonded within the layer, but one layer is decoupled from the next layer so that it's only bonded through so-called van der Waals forces. So the coupling is very, very weak. And our own interests lie in these 6 topics, including the Josephine diode effect. So I just want to briefly introduce these 6 topics, although I won't have time really to cover any of them. But in particular, I wanted to mention then that this diode effect, I'm going to come back to that and discuss some of our work, but these are some of our papers on this effect. And what we were able to show is that we could see a very interesting diode effect by utilizing a special 2D van der Waals material, nickel ditelluride. And later on, we showed we could see similar effects in a closely related material, platinum ditelluride. So I'm going to come back to that. And one of our most very interesting work is a recent work from last year, where we believe we demonstrated that this diode effect we see is intrinsic. It's an intrinsic effect and not extrinsic, as claimed now by many groups. And I want to discuss these 2 experiments after this brief introduction to some of our work on these 2D materials. So unrelated really, is we're also very interested in 2D ferroelectrics. And ferroelectrics, polarization of these materials turns out to be very interesting in these 2D materials. And we actually grow most of these materials not by exfoliation, but by molecular beam epitaxy techniques. And what we were able to show was that we could form extraordinary ferroelectric materials in, let's say, monolayers of tin selenide. And they have a ordering temperature for the ferroelectric polarization several times higher than the bulk material. And similarly for tin telluride. And recently we've demonstrated what we think is a very interesting tunneling junction between 2 ferroelectric domains oriented with their polarizations in distinct directions, separated by a paramagnetic lead telluride. And the lead telluride is just a few nanometers wide. This leads to a very interesting ferroelectric valleytronic tunneling junction device, which again, I don't really have time to discuss. We've also shown the possibility of nano-welding of islands of these ferroelectrics through high lubricity of these layers. One thing that we feel is extremely interesting for racetrack is that we've been able to demonstrate the current-induced motion of domain walls in a 2D ferromagnet. This is the Ein3 germanium tellurium 2. And it turns out that the domain walls are extremely mobile as compared to conventional materials. And we can actually move with current pulses domain walls at very low temperatures, even down to the lowest temperatures, which isn't possible in some of these conventional materials because of pinning of the domain walls. And very recently, we demonstrated an all anti-ferromagnetic tunneling junction using a very special orthorhombic form of a 2D antiferromagnet, chromium sulfur bromine. This is the paper we published in Nature at the end of last year. And finally, this same Nature paper, we showed that we could tunnel through twisted 2D layers, and this twisting destroys the innate anti-ferromagnetic coupling between these layers, allowing us to build very interesting tunnel junctions. And if there's time, I want to briefly discuss our work on twisted junctions for a van der Waals Josephine diode device. Okay, so finally, these 2D materials show extraordinarily interesting topological spin textures, including skyrmions, a wide range of topological structures. In many cases, we've shown that the 2D systems, which are nominally centrosymmetric, have broken symmetries, which allow for the presence of these skyrmions. And those broken symmetries arise from defects in the 2D systems. And this is very, very interesting. And finally, wanted to mention that these 2D layers allow us to explore critical dimensionalities in these 2D systems. We showed in 2021 in this science paper the first 2D XY magnet. And recently we've demonstrated the first 2D spin glass system. So now the final topic I want to talk about is this Josephine diode effect. And this is some work by Banibir Pal, who was a postdoc in my group at the time. And what we did, we took a so-called nickel ditelluride. It's a 2D system, as shown on the left-hand side. You form these beautiful layers of nickel and tellurium. And the tellurium layers on either side of the nickel layer form this strongly bonded structure, which the nickel is octahedrally coordinated by the tellurium. But one layer of nickel ditelluride is effectively only weakly bonded to the next, so through this so-called van der Waals gap. However, what's interesting in the system, and the reason why we chose it is, although it's non-magnetic and not superconducting, nevertheless, this system has so-called topological surface states. It's a so-called type 2 Dirac semi-metal. So on the surface, you'll find states which are actually spin polarized when you pass a current into the system. The current will flow and the spin of the electrons are coupled to the direction in which the electrons flow, so that the spin of that electron will be orthogonal to its direction. So this leads to can lead to spin polarized surface states. This is the reason why we chose this system. Otherwise, this system is a system that is centrosymmetric and non-magnetic. It breaks neither time reversal symmetry nor inversion symmetry. So this is our basic results. What we do on the left-hand side, you can see we take a flake of this van der Waals system, a few microns wide, and then we build on top using standard electron beam lithography techniques. We build niobium contacts. You can see these contacts in the left-hand side, and the niobium wires are separated by you can see the spacing is 120 nanometers, 350, and 580 nanometers. This is the concept. So on one flake, we can build junctions, lateral Josephine junctions, where the spacing between the electrodes is varied. Otherwise, we know that the flake is identical for all of these. And then in the middle, you can see we measure the voltage across two of these niobium electrodes as a function of temperature. And when the temperature falls below some critical temperature, the niobium becomes superconducting. That's the first temperature. Here it's just above 5 degrees, it's about 6 degrees Kelvin. So the transition temperature of these niobium electrodes depends very much on the growth and in particular on the thickness of these electrodes. So these are relatively thin. And then at a lower temperature, we're going to call it TJ, you can see at a lower temperature, the voltage between the two electrodes essentially goes to zero. And this is because a supercurrent now flows between niobium electrodes through the nickel ditelluride. So on the right-hand side, you can see a plot of the voltage between two electrodes as a function of the current. And you can see at small currents, the zero voltage. As the current is increased, then let's say take the blue curve, then as the current is increased, eventually the system becomes normal and the voltage will go from zero to a finite value. And there is some hysteresis because of the capacitance of these junctions. And nevertheless, if you look at the critical current from going from the superconducting state where the voltage is zero to the finite value, and you look on the right-hand side, let's say that's called IC plus, and then you look on the left-hand side, IC minus, you'll see these two values are essentially identical. And we have voltage versus current curves for these three junctions on this same flake, which have separated by 120, 350, and 580 nanometers. And so you can see as the spacing is increased, with 580 nanometers, that's half a micron, we can still flow supercurrent, but the critical current density will be reduced, as you can see here. So in fact, in some other materials, which I won't have time to discuss in platinum ditelluride, we've demonstrated that we can flow supercurrent through that material over more than 1 micron. So it's quite extraordinary that we could stabilize supercurrent flowing through these Dirac semimetals over very, very long distances, which is amazing. And you can also see in the middle that the temperature at which we see the supercurrent flowing through, in this case, nickel ditelluride, will decrease as we increase the separation between those niobium electrodes. So the most important point is what happens now when we apply the magnetic field. Now, we have to apply the magnetic field not parallel to the supercurrent, but perpendicular to the supercurrent. When we apply this magnetic field By perpendicular to the supercurrent, here it's 20 millitesla. Now you can see that IC plus and IC minus take very different values. And here they differ by 40%. This is the device with a spacing of 350 nanometers. If we take the same device with 120 nanometers, then the difference between the critical current for positive flowing current and negative flowing current is about 80%. So this is an enormous effect, a diode effect. And the diode effect is, you can see on the right-hand side, here we show the current flowing between two electrodes as a function of, and we show the current is switched from flowing in the negative to the positive direction. That's a green curve. But you see the red curve on the right-hand side, which is the voltage. And for one direction of the current, the negative direction, it's 0. But for the positive direction of current, it's a finite value. So we have built a diode, a superconducting diode or Josephine diode with an extraordinarily large diode efficiency. As I said, here it's 40%, but for a narrow spacing, it's up to 80%. And we only see this rectification effect in the presence of this small magnetic field. And I didn't mention, but these experiments are carried out at approximately 10 millikelvin in a dilution refrigerator. So this is a wonderful effect, a huge giant diode effect. And so to understand this, we collaborated with Liang Fu and his group at MIT, who were working on finite momentum Cooper pairing. And so the Margarita and Yang developed this model. And basically what they do is they look at the possibility of Cooper pair tunneling and double Cooper pairs tunneling. And by considering this simple possibility, then they can and then in the presence of a magnetic field which is perpendicular to the supercurrent. As I mentioned earlier, we have these topological surface states. What does that mean? That means, as I mentioned, that through Rashba effect, the momentum of the electron is coupled to its spin, or its spin is coupled to the momentum. So when we apply a field perpendicular to the momentum, the flow of the electrons, that leads to a spin splitting of these spin polarized surface states. And so that means now we have an exchange splitting. And due to that, just for the reasons I discussed earlier, the Cooper pairs are now formed from Cooper pairs which have distinct momenta, and this then leads to basically a finite momentum Cooper pairing effect. And what it means is, as we increase, or when the field is 0, there is no finite momentum. As we increase the field, that momentum will increase. So the electrons, as they tunnel, the Cooper pairs, as they tunnel through the Josephine junction, will pick up a phase. And what is extremely interesting is, as you can see from our experimental data in the top left, here delta IC is the difference between the critical currents flowing to the right and to the left. In zero field, they're the same. As we increase the magnetic field up to a maximum, in this case 15 millitesla, you see that the magnitude of the difference in the supercurrents increases. But as we further increase the field, then the magnitude decreases, and eventually it crosses 0 and reverses inside. And as we further increase this magnetic field, we actually see an oscillation in the magnitude of this effect. So what Liang and Yang and Margarita were able to show was that they could demonstrate that this was due to this additional phase that the Cooper pairs pick up from the spin splitting of these topological surface states. And with the increasing field, that spin that increases, and the electrons pick up more phase, and this gives rise then to, through the standard current phase relationship, nodes in the delta IC as a function of increasing magnetic field. What was also very nice was we could calculate, or they could calculate, the dependence of this diode effect, the difference in critical current for left and right, as a function of the superconducting order parameter and how that relates to temperature. And you can see here very nicely that they predicted that this diode effect would vary as the temperature minus the temperature at which we form by proximity the superconducting state in this case, nickel ditelluride to the power 2. And this is, in fact, what we find experimentally, as you can see on the bottom left. Here is the difference in the critical currents as a function of temperature, and the red curve shows this T minus Tj to the power 2. So we could explain basically all aspects of our experimental data, in particular the temperature dependence of the asymmetry in critical currents, as well as the dependence of this asymmetry on the magnetic field. So we think this is very compelling evidence for this concept of the finite momentum comparing, similar to what I discussed earlier, but now not in a ferromagnet, but through the field-induced splitting of the topological surface states. And this is where the finite momentum comes from. So now I want to just, in the last few moments, mention briefly some other experiments. And so in the last 2 or 3 years, we've explored now a wide range of different materials. And again, this is some work by Kunrok Dion when he was visiting my institute. And what we did here was we looked at a lateral Josephine junction formed not from nickel ditelluride, but here actually formed from platinum. And so this is a little bit controversial, but nevertheless, in this case, so in order to see a Josephine diode effect, you have to break both inversion symmetry and time reversal symmetry. This is so-called magnetochiral anisotropy. And so what we find then is that in this case, we break time reversal symmetry in platinum by growing a platinum layer on a substrate which is insulating, but which is ferrimagnet. This is a so-called YIG. It's a garnet, film yttrium iron garnet film, and this is a ferrimagnet, so it has a net magnetization, and turns out you can magnetize that YIG in a direction with its magnetization perpendicular to the supercurrent direction as shown in this cartoon by the white arrow. So the white arrow is the magnetization of YIG, and basically we apply a big magnetic field, you go back to zero, and through the hysteretic effect, then the YIG is magnetized in that direction in zero magnetic field. Now we grow the platinum is on top, and we have niobium electrodes separated by a relatively small distance. And again, the platinum can now become superconducting by proximity to niobium, and it's magnetic by proximity to YIG, and now we see a diode effect. But we see this in zero magnetic field. And so these are some results from this paper of ours from 2022. And on the top left, we're now plotting not the voltage, but the current as a function of voltage between the two niobium electrodes in this lateral device. The current now is flowing through platinum, which I said is magnetized by the underlying YIG layer. And in A, you can see the current as a function of voltage. So again, at low currents, we get zero voltage, supercurrent is flowing. But as you can see in the orange curve, you can see that the critical current at which the system becomes normal is larger for the positive flowing current than for the negative flowing current. That's the orange curve in the top in A. However, if we now switch the magnetization of the YIG, so it's magnetized in the opposite direction, then you can see now we see the green curve, and now the critical current for the positive flowing direction is less than in the negative flowing direction. And by the way, this platinum here is only 3 nanometers thick. If the platinum is too thick, then the double proximity effects, the superconductivity and magnetism will no longer interact. And in E, you can see then this zero field diode efficiency, how it varies as a function of temperature for different thicknesses of platinum, 3, 5, and 10 nanometers. And I do want to point out that the temperature dependence of this effect is very different from the temperature dependence I introduced earlier. Earlier, I showed it varied as T minus T to the power 2. Here, it varies as 1 minus T upon Tc to the square root of that. So it's very different. So the dependence of the diode efficiency with temperature has a very different dependence. In this case, also, we see very large effects. We see up to 35% difference in critical currents at now a higher temperature, 2 Kelvin. Previously, our work was at 10 millikelvin. So these are two very interesting proximity effects working together. Now, finally, in the last few minutes, let me just talk about one other experiment, which is some work we published last year. This is by Jae-Kun Kim, a postdoc in my group. And what he has done is we've now grown a vertical tunnel junction, all van der Waals materials. So here we're using niobium diselenide. 2H niobium diselenide is a very interesting superconducting material. We're using relatively thick layers as the top and bottom superconducting layers. And in between, we're putting layers of tungsten ditelluride. And tungsten ditelluride is a super interesting material for all sorts of reasons, but in particular, it has an orthorhombic structure. And this is very important. So it's a non-centrosymmetric material, and the green plane is a mirror plane that this structure persists. So now what we're going to do is we're going to look at the voltage current characteristics in the presence of a magnetic field. And if you look at the top on the C, you can see the voltage versus current curve. For the case of 0 millitesla, that's the black curve, then the critical current flowing right and left are identical. However, in the presence now of a 6 millitesla field, but now we can apply a field in the plane of this van der Waals material, which is vertical, which is orthogonal to the supercurrent, which is now flowing vertically. So now we can rotate that field in any direction in the plane of this tungsten ditelluride. So here's the example where we see a diode effect. And the diode effect for the green and orange curves, as we change the field from plus 6 millitesla to minus 6 millitesla, you can see that the difference, the diode effect that we see, has changed its sign. So what does it mean? What we can do then is we can measure, okay, I'm going to skip this. What we can measure is here we have three distinct all van der Waals vertical Josephine junctions that Jae-Kun has made. And we actually don't know the orientation of the tungsten ditelluride flake before we do the experiment. So he does the experiment and he measures this eta, the efficiency, the difference between critical supercurrents for left and right, in the presence of magnetic field. On the left-hand side, it's 200 millitesla, and the field is rotated in the plane of the tungsten ditelluride. And on the left-hand side in A, the tungsten ditelluride spacer layer is 2 nanometers thick. In the middle, it's 7 nanometers thick. And on the right-hand side in the C, it's 60 nanometers thick. So in all cases, we see that a sinusoidal dependence of the magnitude of the diode efficiency on the direction of the magnetic field in the plane of the tungsten ditelluride. And as I mentioned, we've got a vertical junction, so we can rotate the field always orthogonal to that current, but we can rotate it within the plane of the tungsten ditelluride. And what we find is then, afterwards, we can then determine the crystal orientation of the tungsten ditelluride. This is some collaboration with Georg Wolterstorff at the Martin Luther University. He has a polarized Raman system. So now we can determine the crystal orientation of each of these tungsten ditelluride flakes. And in each case, we find that the maximum diode effect is when the field is applied along the A-axis, and that axis is perpendicular to this mirror plane. So in every single case, all these junctions, we don't know the orientation, crystal orientation of the tungsten telluride, but after we've determined it, we find that the maximum diode effect is always when the field is oriented perpendicular to the vertical current, but is aligned in a direction perpendicular to that mirror plane. So we've correlated the Josephine diode effect with the crystal lattice of the tungsten ditelluride. And this means that we believe this is very strong evidence that the effect we're seeing is intrinsic to the tungsten ditelluride in this way. So in other words, other groups it turns out that it was known even 20, 30 years ago that in junctions which have a which are geometrically inequivalent, distinct for different directions, then you can basically trap magnetic flux in the junction. And this gives rise to an extrinsic diode effect. And so some groups have claimed, oh, all these effects are extrinsic. But we believe in our cases, we see an intrinsic effect. On the one hand, we believe that because we can account for the complex temperature and field dependence of the diode effect with a finite momentum Cooper pairing model. And on the other hand, in this case of tungsten ditelluride, because of its low orthorhombic symmetry, we can demonstrate that the Josephine diode effect is connected to the crystal structure itself. So now we looked at the temperature dependence of this effect, and at the same time, it also follows this 1 minus t upon tc to the square root 2. We also show that the magnitude of this non-reciprocity increases with the thickness of the tungsten ditelluride up to a maximum value of about 30 nanometers, which is obviously some intrinsic length scale within that superconductor. So I'm just going to skip this. And now finally, I wanted to mention, well, our goal is now to use these two concepts. One, we want to create spin triplet supercurrents in the S equals 1 or S equals minus 1 state and inject those into a conventional racetrack, although maybe from special magnetic materials, in which we could move the domain walls using the angular momentum from the spin triplet supercurrent, which in principle will be a very efficient, energy efficient. And at the same time, we want to build this Josephine diode into the racetrack, e.g. using the platinum-based diode, and then we can detect the domains from whether or not a supercurrent flows through the diode formed between the racetrack and this platinum junction. This is the idea. So I think this is a very, very interesting possibility of creating a cryogenic racetrack memory that would operate at low temperatures. And why do we want to do this? We want to do this because there's huge interest in quantum computing systems where the qubits, whether they're spin or neutral atoms or superconducting qubits, operate at very low temperatures. So low temperatures. And you need logic, memory and logic operating at the same temperature for the most efficient quantum computing system. Today, the logic, the memory that is needed to basically store the settings for each of the qubits, typically they have to be tuned in superconducting qubits, or the output of a calculation, you need to store it somewhere. Then today that's done at temperatures well above the temperature of the qubits, let's say 4K or 77K. If you had a memory device and logic operating at the same temperature, 10 millikelvin, this would make for a much more efficient and more powerful quantum computing system. So this is what we want to do. That's what we're working on. So I'm now going to summarize. I briefly introduced you to reminded you about spin valve sensors. First spintronic device that basically still used in magnetic disk drives, and 80% of all digital data is read using these sensors that I developed when I was at IBM. And now these sensors are replaced with magnetic tunnel junctions using materials that I published in a paper in Nature Materials in 2004. And so today, all digital data essentially uses a spintronic device to read it. Same time, racetrack memory, which I've worked on for many years, but nevertheless, we now believe we have demonstrated it does work in racetracks just 50 nanometers wide, and therefore, technologically, the length scale is such that would enable us to build a racetrack device that would have the same capacity as a disk drive, but be 1,000,000 times faster to access the first bit and 100 times lower energy. And I didn't mention this, but a single domain wall racetrack, we can move the domain wall backwards and forwards at very fast at speeds of a few picoseconds. So this could be a replacement for the fastest conventional volatile memory today, which is static random access memory. But a single domain wall racetrack would be non-volatile. And finally, I mentioned some of our work on the creation of triplet supercurrents, in particular, these long-range triplet supercurrents through a atomically scaled antiferromagnet, mainly 3 germanium, which have a Kagome triangular lattice. And I mentioned we've been able to see very large Josephine diode effects through nickel ditelluride, magnetic platinum ditelluride, and vertical Josephine junctions formed from tungsten ditelluride. And finally, I believe we are on the path to creating a high-performance cryogenic memory, which would, I think, be impactful for quantum computing systems. And so I want to thank you very much for your attention.
Okay, thank you very much, Stuart. So you took up the whole hour. So I hope you have you have some time for questions.
Maybe just we could have a few questions. Yeah, sure.
If there are some questions,
If there
just
are any.
raise. Okay, Vincent, I think Javier, you can. Vincent has a question.
Okay.
Okay, just a second. Okay,
Yes.
Vincent, you should be able to talk now.
Okay, is it working?
Yes?
Perfect. So thank you, Mr. Parkin, for your talk. It was really, really interesting, really impressive.
Oh, thank you.
I have a couple of questions. So looking at your racetrack memories, it's like
Yeah.
you've shown that you can read extremely fast with few pulses, but
Mm.
how much fault tolerant is it? Because when you apply a pulse, you also destroy some domains, no?
No. As we showed many years ago, if you apply a current pulse, you move all the domains in one direction. In the case, whether you use spin transfer torque or spin orbit torque, in the case of spin orbit torque, it works because the interface between the magnetic layer and platinum gives rise to an interface vector exchange, an interface Dzyulinski-Merea exchange that forces the domain walls to be a chiral domain wall. Only for this reason do all the domain walls, because of that chirality, they will all move in the same direction through the spin orbit torques created by converting the charge current through, let's say, platinum into a spin current. In the case of spin transfer torque, it relies on the current being spin polarized through spin-dependent scattering within a magnetic layer. And so let's say you have a domain wall going from up to down, then the current is polarized up in the domain and then causes the domain wall to move to the right. And then the next layer, it's polarized down, and the down to up domain will also move in the same direction. This is something we showed in 2008. So in both cases, the domain walls move in the same direction.
Okay, and I also have many questions, but maybe someone else, if there's someone else.
No, there is. Wait a second. Yeah,
Max,
Max.
just a second. Okay, should be able to talk, Max.
Hello, thank you very much for this talk. I wanted to ask how much current, how much, let's say, triplet current do you need for this movement of the domain wall? So how large should be a critical current of these materials?
Now, this is a very good question. And currently, the critical current densities would not be sufficient, let's say, move a domain wall in conventional magnetic materials like cobalt, nickel, cobalt. So you have to, as I said, you need to find new magnetic materials with lower magnetization. And this, of course, is possible. This is something we're working on. So I think then there will be enough, in principle, enough triplet supercurrent to move the domain walls. This is the most interesting question. How do you generate, on the one hand, large triplet supercurrent densities, and on the other hand, have a magnetic material with sufficiently low magnetization that you could, let's say, move a domain wall. So this is the key question.
Okay, thanks.
Is there more questions? Vincent, again? One more question, because I think
then I have to go. Yeah.
Yes,
Just
yes.
one question. Okay, so I have to choose mine then. That's many. So it's like you shown that for the spin diode effect, it was highly dependent on the crystallinity of your sample and on the other parameter. It's like what will happen if instead of having like a flake which is highly crystalline, you will have something which is polycrystalline in your mind? Will you have like a rounding and then you have the effect in all the direction of the applied field, or will you destroy totally the effect?
No, it turns out even if it were polycrystalline, it would behave the same. This, let's say, the Reshbar effect. Basically, we need the electron spin to be coupled to its momentum. It's irrespective of the direction in which the electron travels. So that would be the same in all the polycrystalline materials, except in the case of tungsten ditelluride for the vertical junctions. Then in that case, as I showed, we have a very interesting dependence on the direction of the current, or direction of the magnetic field in that particular case. But usually it would not be important.
Okay, thank you.
Okay, so maybe there are more questions. You may send an email to Stuart.
Yeah, please send me an email.
Yeah, he has not to leave. So let us thank Stuart again. Thank you very much for your time.
Yeah, thank you very much. It was a great seminar, very
Great
enlightening,
seminar, great talk.
and very inspiring.
Yeah.
Well, thank you. Thank you again for inviting me. I'm happy to give the talk. And as I said, as you said, anybody who has a question there, welcome to email me. You can find my email on my website.